Hello everyone. So it's 5 o'clock, so we are all exhausted by those many talks. The Spring I/O is about to end soon. So I'm very happy to see so many people here in this room still and who are interested in fuzzy search with Postgres. And also it looks like my clickbait title worked out. So actually, after this talk, you cannot really throw away your Elasticsearch if you're already using it. But maybe I can show you some cases where you don't need to introduce it. Okay, so my name is Thomas Gräfenstein. I'm from Germany. I'm a software engineer working for Eon One. Maybe you have heard of Eon. It's a big corporate in Germany in the energy sector, but Eon One is a company who provides digital products for the energy market. So I'm working in an environment where we are basically iterating and incubating products, and most of the time we are starting on a green field, which is really nice. But this also leads to a fast, or the requirement of a fast time to market. So I'm just saying this because this will set the tone of the whole talk a bit. Yeah, I work with in the JVM ecosystem with Java and Kotlin and Spring since 2017. Started with Java and then over time transitioned to Kotlin because for me personally, I really like it. It's really nice. And in my current position, I'm also not just developing, but also leading and mentoring development teams. Okay, so who of you ever has used a search? Everyone? Who was at some point frustrated because the search was not really working well? Also really a lot of people. Yeah, so let's introduce a case. Let's suppose we have a kind of system which stores customer data and an agent needs to somehow search on this data. What is a customer? A customer can contain some kind of personal information, address information and whatnot. So you name it, a lot of information can be linked to a customer. And since I'm from Germany, I introduce some, here you can see some examples how you can spell a name. So Philipp Meyer is a really common name, or the first name is common, the last name is common, the combination maybe not so much, but it really shows perfectly how different the same name can be spelled. So if you say over the phone, yeah, my name is Philipp Meyer, yeah, there you see how unprecise natural language can be. Because you don't know, is it with one L, with two P's, or vice versa, so there are many variations. And on the other hand, if you look at the address, there are also the possibilities of variations, but also typos and misspellings. Yeah, so in Germany we have this awkward looking S, which looks like a B. So you can also, if you don't have this on your keyboard, you can instead use double S. You can use the dot to shorten it, or in the last example, it's actually a typo because yeah, Straße always needs two S, or this scharfes S, so the big S in German. Yeah, so some side fact about German language. Okay, we can derive some requirements to our search. So as we have seen, we maybe want to search on the first name, on the last name, maybe on some kind of address attributes. So to sum it up, we want to search by a set of attributes. The search needs to be error tolerant. What does it mean? So especially if you work with some kind of user-provided input, you need to deal with those variations and typos, misspellings, and whatever can lead to variations of the input or the data. Also, what is trivial, I guess, but the search needs to be case insensitive. search needs to be fast. So you don't want to wait a couple of minutes or hours even until your request comes back and returns a result. So yeah, this really depends on your use case, what fast actually means. What else? The search needs to provide relevant results. So if you search for Philip, you don't want to get a result back for Antonio, for example, right? And the search, in our case, needs to be or should be independent from natural language. I will explain it in a bit what it means, but it would be nice that you don't need to implement your search algorithm or approach per language. So ideally, it scales with every language you introduce in your system. So let's have a look on some naive approach. So with Postgres, you have this like operator or I-like operator for the case insensitive search. And if you want to really shorten it up, it's like a really basic form of regex search. So you know how to match patterns with regex, but this is not regex, just to be clear. So we only have two possibilities. First one is the percentage sign, so it can match 0 to any amount of characters, or the underscore, which matches exactly one character. So we are here in Barcelona, so is Barcelona like Barcelona? Yes, of course it is. If you want just to search for the beginning of a word, you could do something like this. So search for bar and the percentage sign. So is Barcelona like bar percentage? Yes, it is. Is Barcelona like Elon? No, of course not. Because here we just use the underscore. So you get how it works, right? Okay. So let's revisit our requirements. And just by looking at the traffic lights, yeah, we achieved already a lot, right? So let's go through them. We can search by a lot of attributes just because we are using SQL. Of course, we can search and apply this operator on many columns. The search is error-tolerant. If we mean we can deal with typos and misspellings, I would say no, not at all. Because really you need to predict the search input, or you need to have some kind of structure on your data you want to search on. And this is not really the case if you work with human-provided data and human-generated content. So yeah, in the end, human errors are not predictable, right? If they would be, we would not have typos. So how long does a computer exist and a keyboard, and still we are doing some typos, right? So we are not perfect. So at some point, we as humanity, we reach the peak. So we need to deal with this with software in the end. Yeah, search is case sensitive with the I-like operator. Sorry. The search is fast, or at least it can be fast, because Postgres offers two types of indexes here, gist and gin. I will explain later what it means. And this is also applicable for the like operator. Search provides relevant results. I marked it as green because it really depends. If we say our scope is only for predictable patterns, yes, it really is. I will come to it in a minute. And search is independent from natural language. Not really, because if you again look at this example, I mean here for city names, you can question it if you need to implement those pattern matching per language. But if you look or remember the address from before, so Köln is Cologne in English, so it's a completely different word actually. So yeah, you cannot really make useful use of this operator. Yeah, so where then could you use it instead? Where is it a good fit? Why I'm talking so much about this simple pattern matching? Yeah, you might have cases like a contract number. So if you think back of this customer example, a customer usually has a contract number or some kind of human readable number, which has a predictable pattern. So maybe you have a CN for a contract number, some characters for the date or for the user ID or something which uniquely identifies the user by the customer number, and other examples, right? So if you want to just search for all the phone numbers in Spain, so you just search for the 3, 4. If you want to find all users which have a Gmail account, you could use this pattern and file path. So what I want to say here, it really depends on your use case, what you are searching on. And for this, yeah, use the right tool. So coming back to where we want to, or how can we improve this? So if you have content which can has errors and typos. So here I would like to introduce the idea of trigrams, and from my research it's very unique to Postgres. So what is a trigram? It is a group of 3 consecutive characters taken from a string. We can measure the similarity of 2 strings by counting the number of trigrams they share, blah, blah, blah. So let's have a look at the example. So if we want to calculate the trigram of hello world, we see, okay, we have a set of strings, and each of them has the length of 3. So this is how the name, or where the name is coming from. And to ensure this constraint, when you start looping through the word or iterating, you have to prepend the first 1 and 2 characters with the space. This is how it works in the end, until you reach the end of the word, and this is your trigram, basically, or your set of trigrams. Yeah. How does it help? So you can then start calculating similarities based on this trigrams. And Postgres offers the similarity operator. And the output is the number from 0 to 1. So 0 means no similarity at all. 1 means 100% similarity. So a perfect match. So let's go through some examples real quick. So hello world is exactly, it's equal to hello world, of course, so it's 1. Hello is equal to hello world with a similarity of 0.5, so 50% similarity here. If you look at by world compared to hello world, the similarity drops. Why is that? Because now the set of trigrams for the by world string is increasing, so the actual matching trigrams relative to the total number of trigrams is dropping. Yeah, and in the other example here, you just have the end of the word, but not the full one, and it has even lower similarity. So, just as a rule of thumb, you can just ask yourself, are these 2 words kind of alike overall? So this operator is like, you can use it in any direction, so it will just compare the similarity between 2 strings. Yeah, this is good, but it can be better. So the next one is the word similarity operator. And compared to the previous example, we directly see here, in the second case, we increased our similarity from 0.5 to 1. So we have a perfect match. Why is that? Because now we start comparing per word. So if we split the second string into 2 individual words, yeah, the first one is a perfect match, and the second is no match at all. So we just take the one with the highest similarity, and this is our total output. So I think you get the idea. Or how you can also think of it, you just take your word and slide it over the second one, and you just take the one, or you just find the highest similarity, and this is your output eventually. Yeah, and for the sake of completeness, there's a strict word similarity operator, which does the same, but it respects word boundaries. So you cannot just slide it over, but it has to really fit into the same word. So looking at the last example, the similarity actually drops again, because now it takes the whole similarity and does not take the highest in general. So I would just recommend take this and play around with your data. And depending on your typical search behavior in your app, you then decide which one to choose. There's no rule of thumb. You just need to understand the concepts of those operators, and then pick the right one. So you can also mix them with different ones and write a perfect query for your use case. Yeah, but we are in SQL, so having those long function names, let's say, is not really convenient. So we don't want to really work with number outputs. In the end, we just want to know, is a word similar or not? So basically, here are the actual operators you can use in your queries. So with the percentage, smaller than and double smaller than sign percentage. And because of the nature of those operators, they have different thresholds. So what does it mean? If we search for all customers where Barcelona is similar or equal to the city, it can be it is equivalent to this query, and those thresholds are the default set by the database. Yeah, a question to you. What do you think? Which one can make use of indexes? The first one? Okay, not many. The second one? Okay, you're not really sure. This is not a problem. So actually it's the first one, because here Postgres can basically make use of the defaults and does not need to calculate it every time. So you can really make use of the index. Maybe it doesn't sound like a good explanation, but in the end, it's due to the nature of those thresholds. But it can be that in your case, those thresholds are too low or too high. So what does it mean if we are not reaching, in the first case, the 0.3? So we are below. Then actually we don't yield a result. But maybe in your case, it makes sense to still return a result. So you want to lower it. And just that you have seen it, you can do it system-wide. You have two possibilities how to configure it, and then you can override the default for the whole database. And what is my preferred option, you can do it per database, because then you do not influence any other databases in your system. Important to know, this only comes into effect for all new connections. So if you start your application again and every connection is lost, then Postgres will again use the default value. So keep this in mind. I've talked about indexes, gist and gin. What do they mean? So we have a search tree based index and inverted based index. So how do they look like? So just to get a feel, what's the difference? So gist is basically a tree, B tree. You probably know what it is. So we can organize our cities into north and south, and then again go down, and then Barcelona is the northern city, Malaga is in the south, and Madrid is somewhere in the middle. And gin indexes, on the other hand, they are basically like a lookup table. So Barcelona appears in row 1 and 3, Madrid in row 2, and Malaga in row 4. So these are under the hood the differences between the two index types, and depending on your case, it makes sense to use one or the other one. But in the end, we are lazy, right? So we just want to use a fast search and want to guarantee it performs well. So I usually like to understand the behavior behind, but for us, we just need to know some facts about those indexes. So due to the nature of those indexes, index lookups are usually 3 times faster, because we just go there and have one lookup, and the gist index has really to traverse the tree. But this also has the side effect that GIN indexes are 2 to 3 times larger than gist indexes. And yeah, just for the same reason, it also takes longer to build them and slower to update them. So you could think, okay, GIN index is probably a bad idea because of those disadvantages. But here again, it really depends on your use case and your application. So I again want to provide some rule of thumb here. So you can use GIN indexes for static data. There they work really good, because static data, like customer data, doesn't change too often. So you just insert it once and it then rarely changes. And gist indexes are really good for data which is updated on a regular basis. So yeah, keep this in mind when adding indexes. Okay. Then let's revisit our requirements from the beginning again. Yeah, the first one is again a check. Second one for me again is now is green, because we switched from a pattern matching approach to a similarity matching approach. In the end, we are transforming data to or our queries to similarities, and in the end we just compare similarities and numbers, so they are really abstracted from the human language. And since the threshold is configurable, we can also configure our error tolerance. So let's say we want some kind of fuzziness where we want to cope with some errors, but not too much, because then we would yield too many results or too many not relevant results. So really, it also depends on your users. So if they are really good in typing and searching and are already really precise, you can probably just upper this threshold a little bit. On the other hand, lower it again. Yeah, case insensitive, sure. Search is fast, here again, by the support of those indexes. So this is nice. And the search provides relevant results, especially in layer 8 scenarios. Yeah. So layer 8, anyone knows what it is? This is layer 8. So the layer in front of the screen. Okay. Good. So I will end the slide mess now. And let's have some fun and see it in action. You see it, right? Okay, perfect. How can I switch the light mode?
Settings, appearance. Open the settings, and there is appearance first.
Okay.
Command. Appearance. The first line, appearance.
Ah, yeah. Okay. Thanks.
Opening. Appearance, under it. Appearance is the second line.
Ah, okay. Yeah. Ah, okay. Yeah.
Switch to
Yes. No sync, please. Thanks. Yeah, I really prefer dark mode. Yeah, so hello. Wake up, please. Okay, some things are still black thanks to IntelliJ or my bad. So now this is a perfect example of layer 8 problems. Okay, so I implemented a demo application to showcase how to work with it in a Spring application. Since we are on a Spring I/O, yeah, let's have also the use case how to use it in Spring. So far, what I have explained is Postgres only, right? Yeah, so I have built a demo API where we can request some customers. And since my database is still empty, I don't get any results back. So in the background, I'm using Docker Compose, Postgres, Starter, and so on. So let's populate some data. Here, thanks to ChatGPT, I can create customer data. Is it big enough? Yes? Okay, perfect. Yeah, so this is a really naive script to generate test data. If you need better test data, there's a lot of tooling out there, but this is sufficient for our case. So what we are doing, we are creating a customer or a lot of customers with different addresses and names and contact details. So let's execute it. Perfect. Let's execute our request again. And it doesn't provide a result still because we already provided a search input. But if we now say want to search for Barcelona, yes, we get elements back. Okay. Yeah, so what did I do to show this? So we have a customer table. It's very simple just for the sake of the demo. So we have a contract number, the address attributes, contact attributes. And this API is already making use of this similarity operators under the hood. So let's say I have a typo. Yeah, we still get results back, so it means for me the API is still working. Let's have a look on what Hibernate is doing with this. So how do the queries look like? Since this is a paginated endpoint, we have two queries, those two. So we select the customer, and here the where query begins. We have parameters here, which is nice. So basically this like a prepared statement, and in the end we count the total results for our page information. But how could we achieve this? For this, we need to provide a custom function to Hibernate. Yeah, so yeah, for this you need to implement the function contributor interface. By the way, I'm using Kotlin here, but I think you still understand if you don't know Kotlin what happens. So in the end, what I'm doing here, I'm providing a contributor to let basically JPA and Hibernate in the end know how to work with this operator. Why is that needed? Usually, if using JPA and the JPQL language, most of the operators you know and you're familiar with are supported, right? Or basically all. Yeah, the reason is trigram is an extension in Postgres, and as far as I know, as I said before, no other database is supporting this in the exact same way. So of course, it's not adopted in the framework. But we can extend it. That's not a problem. So what do? We provide the custom SQL function. So I will use the word similarity operator in this case. And it's pretty simple. We just walk through our arguments, accept them, concat them with the operator, have the brackets, and that's it. But just defining it is not enough yet. So you need to do another step. So you need to provide a file in meta-inf services, which is the full qualified name of your class of the implementation. And then on startup, Hibernate will check this location, pick it up, and then you basically extended Hibernate. Yeah, then let's have a look on our repository. Here it now becomes interesting because you have multiple ways of using this in your application. And I will show you 3 ways of doing it. I have a favorite, and I will also tell you why. So the first example is using JPQL. So if we go back to our implementation, what I did actually, here I gave my custom function a name. And this now I can reference in my JPQL statement. So I will select a customer, and in my example, I'm just searching for the first name, last name, city, and street. You can use all the JPQL statements and queries, how you are used to it, just that this one is basically now added to your query, or to your query language. Then what else can you do? You could use a native query, then you don't need all of this. You just write your query as a native query and use the actual operator. So this example is better readable and very nicer because then you know where it comes from, right? So if a new developer in your code base comes and sees this query, I have never seen this operator before. What is it? Quick Google search. Okay, sorry, ChatGPT search. Then probably it will tell you what it is. And then some of you may have noticed we extend or we implement the specification executor. So you are also able to use the criteria builder in Spring Data. Who of you has ever heard of this? Specifications criteria builder? Okay, some of you, but not everyone. So let's show the consumer side. So for the first one, it's pretty simple. So here we have the search service, which connects to our repository. And in the first example, it's really easy. We just provide our search input, pageable. We can map it to our DTO projection, and that's it. And yeah, coming to the specification, thanks to Kotlin, I can write the extension function. And this now becomes interesting if you want to create dynamic queries. So let's say you have some kind of business logic, and depending on this, or maybe you want to write some limited search syntax, which is not just accepting a string to search, but some kind of second query parameter to really steer the search. Then you, based on this, you could provide different paths, in this case, or predicates on which columns to search for. In my case, to have the equivalent example, I'm using the same fields again. And for everyone, for every of these, now I can call my function via the criteria builder, and in the end, it's a OR match. So yeah, compared to this, my personal favorite is just use JPQL, because then you are also not bound to raw SQL, you are not bound to specifications. And there's another caveat when using specifications. So let's call the specification endpoint, submit request. Now the query looks different, and we see the actual search input. So why? So I mean this. So maybe let's replace this example with a more readable one. So again, because this is auto-generated by IntelliJ. Yeah. So we see our search input is showing up in the queries, and now the alert bell should be ringing if you think of SQL injections and so on. Then this is really not a good thing. We definitely should change this. So yeah, since we are still using Hibernate, from my research and my tests, we are not really affected by SQL injections here, because Hibernate will still take care of sanitizing this input. But there's another caveat. It's not a prepared statement anymore. So if you just use, maybe I can, so I hope you can see it better now. If you use the parameter version, then the query planner of your database can make use of it. So this is nothing new. Postgres just adopts the same. So if you always use the same query with a prepared statement, over time the database is learning how to perform those queries, how to optimize the query plan based on your data, and so on. And with this second version, where we have the raw string as a part of the query, then this is not possible. Because from database perspective, this looks like a new query every time. So why is that? Let's come back to our contributor. Implementation, oh no. Sorry, it is a specification. Here. Yeah. So in our criteria builder, we used the literal operator. So what it does, it just takes the input as it is and injects it in your query. And from my knowledge, Hibernate is able to let you provide parameters, but Spring Data JPA is not. And I didn't find a way besides really serving my own repository implementation. This didn't feel right, so I will not show it here. But I want to make you aware of it. If anyone of the Spring team listens to this, maybe takes this as a bug report or as a feature request, since it would be nice, but also we have to be clear on this is a very unique requirement, right? Usually you don't go and extend your Hibernate, you just take the default functionality of your database, right? Okay, so just to prove that all three versions in the end are actually working and provide this the same results, let's have a look at our tests. So we are calling those endpoints, so /customers, /specification, customers, /native. And all of them are green, and you can trust me, I am always using the same search input and doing the same assertions. So technically all three works, but I would just recommend using the JPQL version or the native query, but not specification. Okay. So maybe you came to this talk and thought, I can replace my Elasticsearch or everything I had to implement a search. I hope it's clear that this is only suitable for this specific use case where you want to have some kind of fuzziness. If you have other search requirements, you can and should use different approaches. So regular expressions, I told about it in the beginning. I really don't like them because it's really hard to remember the syntax. For me personally, I don't know how it's for you. What is more real-world proven and production ready and safe, especially in Postgres, you can provide a full text search with the use of TS vector and TS query. Yeah, since AI and RAG and vector search topics arise, and you hear a lot of them everywhere, so we are also at some of those talks here at the conference. It's anyway worth looking into it, how vector searches are working. Just know that in this case, this fuzziness requirement we had is not really offered there, right? Levenstein distance. So here we can calculate the distance from one word to another one. I would say, yeah, I heard the last time of it in university. I never heard of it that someone is actually using it in production, just as a raw search algorithm. Okay, one hand raised. So someone did. And of course, please don't get me wrong, you are allowed to use Elasticsearch or Opensearch. Please do it if you have the right requirements. What I just want to tell you, if you already have a Postgres, you want to provide some kind of search functionality, maybe it's a better idea to start simple and not introduce yet another tool which needs to be operated and maintained. People need to learn it, so this can be a quick starter for your projects. And over time, if requirements changes or you see the actual need for such a system, like a real search engine, then you can still switch, right? Okay, that's it from my end. The whole source code you can find on GitHub. In the same repository, I will put the link for the slides after this talk. You find my LinkedIn. And yeah, the rest what I have to say is thank you. If there are some questions, you can stay here. I'm also here. So yeah, thank you.